Now that we've created these points, which represent the elements or the potential plot locations in the sample, we don't have to draw the line, but we drew the line so we can kind of visualize it. What we're going to do is we're going to break this line, this fractal, into segments, and from within each segment we're going to randomly select a point. In order to do that, we have to first do a few things. We have to add an attribute index. So if we open up our attribute table, we can see that there is an order value that was created. We want to make that the index value. What an attribute index does is it just makes sorting and other queries in a database faster. So we have to find the add attribute index tool. And the way we do that, I'll close this, is I hit the Control F button and I say attribute index here, searching for the tool. And we open that up, and there's a very simple thing. We choose the points, and we choose order value as the field that we want the index to be. After we run that, it runs for a few minutes. We're ready to proceed to the next step. I've already run these steps. So the next thing we want to do is we want to sort this file and create a sorted data set, and we want to sort by so that the records in the attribute table are organized in the order of this fractal. So this line starts maybe in the upper left or lower left corner of the study area, and it works its way continuously across the entire study area. We want the attribute table to be sorted in the order that these points are connected. So I will search for the sort tool. It's in the data management toolbox. Our input data set is going to be these points. The output data set, I've already run this, so I choose, if we look, I'll name it this, but I'm not going to change it because it'll overwrite it. And the field I want to use is that thing I just indexed, which is the order value. And we want to sort it in ascending order. So then I'm going to run this, and after it's done running, we will have a duplicate of the other file. And what you can do is with the output of this, you have to proceed to the next step, which is to open up the attribute table again of the output file, which was just created, and you need to make a new column. I've already made these columns, so you can ignore them. But the way you add a new column, let's pretend this hasn't been made yet. You just open the attribute table and you click here and say add field, and it's important that you call it cluster ID, just like that. It has to be exactly like that for the next tools to run. And I always make it a long integer. So if we say OK, that new column will be made, and it will be filled with blanks. So what I want to do is I want to calculate a cluster ID, which is going to be the segment of each of the lines from within which I'm going to choose points. I want to calculate a cluster ID using Visual Basic code and the field calculator dialog. So I'll right click here and I will choose field calculator, and you just have to follow these steps in order carefully. The parser is going to be Python. We want to show the code block, and we're going to paste in some Python code that I wrote, and I'll have that in a text file available to you. It's not critical that you understand everything that the Python code is doing, but just very quickly, here we're initializing some variables. I'm defining a function. I'm saying that the variables that I'm going to be defining are global, meaning they can be accessed from everywhere. I'm just defining a starting value and an interval with which I want to increment the record ID or the cluster IDs. I have a capacity number here. This capacity number is a little bit strange, so I'll move this aside for a second so you can kind of see that in our file we have 4,499,308 potential plot locations, points at the nodes of this line. What I need to do is figure out how many points are going to be in each of my clusters. The way I do that is I'll open up my calculator here, and it's just a simple calculator, and I will type in 4499308 divided by the number of plots that I want. I want 335 clusters because we know in this example we want 335 points. If I'd wanted 500 points, I would divide by 500. If I wanted 100, I'd divide by 100. The output is a real number. In other words, it has decimal places. What you need to do is write this number down. And I'll just write down 13430, and I'll truncate the rest. It doesn't really matter if you round up or not in this case, and I'll talk a little bit about that later. But just remember, you just need to write this number down. This is the capacity. This is the number of points in each of my clusters, and I think it'll become more obvious later. I've already filled this in, but you'll need to edit this if you have a different number of plots, which you probably will if you're not doing this specific example. So anyway, we have some if-then logic or if-else logic that goes incrementing the cluster ID once we've gotten up to 13,430, resetting the total number of points in each cluster once we've achieved that capacity value, and we end up incrementing the cluster ID, which this thing which gets output by the function, this rec variable, changes when you move on to a new cluster. So I don't want to go into too much detail here, but you'll have the ability to study the code, and I can explain that later. And then finally, once you've pasted in the code and edited the capacity, you just put here what it is that you're doing. And what you're doing is in the cluster ID field that you just created, you're going to implement the autoIncrement function that you've defined up above here. And it's that procedure I just described of going to a record, figuring out if is it the first record, yes or no. If not, go on to the next record and increment the total. Keep checking the total until it gets up to the capacity we just talked about. Once it's gotten to the capacity, increment the cluster ID up next to the next one, proceed to the next row, etc., until you get to the very last row. So after we run this, what you'll see is that there are 13,430 rows or points, which are cluster 1. So this is the first 13,430 that you've encountered along that line that I just described. And it'll go on and on and on until we get to the very last record. And you'll see this is the bottom of the row, the bottom of the file. You'll see that it is 335. Now it sometimes happens that, let's say I had asked for 334 points or 360 points or whatever. It might only have a couple of points here in the very last cluster ID, or it might not actually arrive at that. And it has to do with whether or not I truncated or rounded that number, that capacity number that I calculated in my calculator. So if, for example, if you recall, it was 13,430.7, I just truncated it and used that as my capacity. If this were to be 334, just because of the nature of how the clusters get formed and then the even odd number of points in the study area, I might need to round that up to 13,431, put that as my capacity, and then rerun it, and until I get the correct number of points I originally wanted. That rarely happens, but if it does, just be aware that that's the reason, is that the capacity value and the fact that there's even or odd numbers of points might cause it to not get to the exact number you wanted. So anyway, after I've run that, the next step is to if you want to, try to visualize what these clusters look like. So what I did earlier on this file is I classified it. I classified the symbology using a quantity color ramp. So basically that there's a different color, a graduated color, for each of the 335 cluster IDs. And I won't do it again, but I won't draw it because it takes forever to draw, but I will show you a portion of it and you get a sense of what's going on. So you will probably find that if you try to draw the points, it takes a very long time to draw, just for display purposes. In other words, it has nothing to do with the analysis, but just for display purposes. You might want to run the tool point to raster, and we'll find that by doing the search, and we will choose the point to raster tool. And when you get this tool, you will choose the sorted point coverage with the cluster ID added to it as the point coverage. The field to choose is the cluster ID that you just created. And I already ran this, but you can see here I just made a file with a descriptive name and a .img extension, which makes it a little cleaner. And then I just leave the rest as the default except for the cell size. If you recall, we did our original grid of points based on a 20-meter cell size, so that's why I'm putting 20 here. After we run this, and it takes quite a while to run, so I wouldn't recommend doing this unless you really want to visualize the points, you will get a coverage of a raster coverage where each pixel value is the cluster ID associated with the point coverage, with the sorted point coverage. So what I did was I chose unique values, and it gives me an error saying, oh, there's too many unique values, and that doesn't matter, just for display purposes. So I just say fine. It runs for a little while, and then you can say OK. And then when you display this, what you will see is the actual spatial representation of the cluster IDs. And now you can see how as the fractal moves across the landscape, it goes creating these spatial zones, which are relatively compact, which are all of exactly equal area, including the ones on the edges, and are spread across the entire study area uniformly. So it's kind of nice to be able to visualize these, and if we zoom in a little bit, you can kind of see what we've got. So it's the very final step, and again, I'll just sort of repeat this. We will go back to the partitioning tools, the random point selector. If you remember, we will choose the sorted points as the input. And for an output, we will choose a file. And again, I think I showed you this. I called it random 335, and it must have within it the cluster ID field that we created in the spatial order when we constructed that file so that it has that. After we run it, we will get our random 335 output file. And if we zoom out a little, or a lot, you can see that these points, there's one point within each of the clusters. And that is how the points are selected across space. Now you might look at this and say, oh, there's 2 points. These are 2 different clusters because they just happen to be the same color. You have that happen once in a while. But you can see in this pink area, there's no other pinks surrounding it. There's only one point in the pink area. As you scroll across the area, you'll see the same thing. One point in this whole green area. This little point is in this dark green area, etc. So that's the entire process.